So in this problem, we have a proton that is traveling to the right at 2.0 times 10 to the 7 meters per second. It has a head-on, perfectly elastic collision with a carbon atom that is initially at rest. So we have our carbon atom here, initially at rest. So it has a mass that is 12 times atomic mass unit. This guy has a mass of 1 atomic mass unit. And this guy originally has a velocity of 0. They're perfectly elastically colliding. So after our collision, we have the proton is said to be bouncing back with a speed of 1.692 times 10 to the 7 meters per second. This guy's still 1 AMU. And we want to know our carbon, 12 AMU, is going to go this way with some unknown velocity. So we want to find the velocity of our carbon atom after it was shot by a proton. So we have to use initial and final momentums. So we're going to do proton and carbon before. Let's keep it separated. So the proton before has a mass of 1 AMU and a velocity of 2.0 times 10 to the 7 meters per second. In order to get its momentum, so we're going to call it P of the proton initially, is equal to 1 times 2.0 times 10 to the 7, which is 2.0 times 10 to the 7, and our units are AMU, meters per second. Our carbon has a mass of 12 AMU and an initial velocity of 0. So P carbon initial is equal to 0, which gives us our initial momentum, which is P proton initial plus P carbon initial. And that is 2.0 times 10 to the 7 plus 0. So 2.0 times 10 to the 7 AMU meters per second. So the good thing about these problems is if you have all of your masses and velocities in the same units, since momentum doesn't have a derived unit like newtons, you can leave everything as long as you label it in these weird units. AMU meters per second doesn't have a meaning, but it's really easy because we don't have to convert our units. So let's move on to our final momentum. So we have our proton, which has 1 AMU, its mass doesn't change. And now it's moving at negative, because it's going to the left, 1.692 times 10 to the 7 meters per second, which means that it has a proton's final momentum is equal to 1 times negative 1.692 times 10 to the 7 meters per second, which is 1.692 times 10 to the negative 7 meters per second to the left. The carbon has the mass of 12 AMU, and it now has a velocity which we don't know. We're just going to call it V. So P carbon final is equal to 12V. So that means, kind of intruded on my space a little bit, the final momentum total is the sum of the proton minus 1.692 times 10 to the 7 plus 12V. So our final momentum has an unknown in it. So now we're going to use the law of conservation of momentum. Pi equals Pf. Pi is 2 times 10 to the 7. Pf is minus 1.692 times 10 to the 7 plus 12V. So algebraically, all we have to do is add 1.692 times 10 to the 7, 0.692 times 10 to the 7 to both sides. 3.692 times 10 to the 7 is equal to 12v, because these guys cancel. So then we divide both sides by 12, and we get our final answer, which is 3.692 times 10 to the 7 divided by 12, which is 3.08 times 10 to the 6 meters per second. And since we kept our signs correct, that means this guy is in fact moving to the right, which makes sense. If you fire a proton at a nucleus, it will cause the nucleus to move to the right, and the proton, we said, bounced back. So remember, this was negative. So next week, we will learn how to find this without being told. But for now, we can only find the speed of one of them if we know the speed of the other.